Welcome. Today, we're pulling back the curtain on one of the most powerful lines of code in all of Kubernetes. Type load balancer. It looks so simple, right? But believe me, what's happening behind the scenes is anything but. So let's set the scene. You've got your application, it's all containerized, running beautifully inside the Kubernetes cluster, but that cluster, it's kind of like a walled garden. It's fantastic and safe on the inside, but totally isolated from the outside world. So the big question is, how do you open the gates? Well, Kubernetes has an answer that seems almost too easy. You just add this one little line to your service configuration file, type load balancer, and boom, you're supposedly connected. But of course, it's not that simple. That one line is a massive abstraction, a promise. And what actually happens when you make that promise? Well, that depends entirely on where your Kubernetes cluster is actually running. Let's dive in. Okay, the magic really begins with this component called the Cloud Controller Manager, or CCM. The best way to think of it is as a dedicated translator. It lives inside your cluster, and its whole job is to listen to what Kubernetes wants and then translate those desires into real API calls that your cloud provider like AWS, Azure, or GCP can understand. And this translator is always working, running in what we call a reconciliation loop. It's constantly watching. The second it sees you've created a service of type load balancer, it jumps into action. It calls the cloud provider's API to provision an actual physical load balancer. The cloud then reports back with an external IP address, and the CCM updates your Kubernetes service with that IP. And it never stops watching, making sure the real world and the Kubernetes world always stay in sync. Now, here's where it gets really interesting. That type load balancer request, it's like casting one single spell, but each cloud provider has its own unique way of interpreting that spell. They all give you a load balancer, but the flavor is totally different. Let's start with AWS. Here, the critical choice is how traffic gets to your pods. The old way is instance mode. Traffic hits the load balancer, then gets bounced to a random node, and then finally to your pod. That extra hop adds latency and, crucially, it can hide the user's real IP address. The modern way, IP mode, is way better. It sends traffic directly from the load balancer to the pod's IP. It's faster, more efficient, and gives you the visibility you need. Over in Azure, the first thing you have to decide is which SKU to use, basic or standard. And honestly, this is a no-brainer. The basic SKU is a legacy option that's literally being retired. It has no support for availability zones, and it's open to the internet by default. Yikes. The standard SKU is what you want. It's built for high availability, it's secure by default, and it's the only real choice for production. And on Google Cloud, the big evolution is toward what they call container-native load balancing with network endpoint groups, or NEGs. This is a game changer. Instead of the load balancer just knowing about the big server nodes, it's now aware of the individual pods. This means way smarter traffic distribution and much, much more accurate health checks, because it's checking your app, not just the machine it's running on. Okay, so all this cloud magic is great, but it is definitely not free. And if you're not careful, using type load balancer can lead you straight into two major traps. One is going to hit your wallet hard. The other is going to break your application's logic. So let's imagine you're building a pretty typical modern app. You've got, say, 50 different microservices. The easy, convenient path is to just give every single one its own type load balancer service. But what do you think that actually costs? Yeah, you're looking at almost $1,000 a month. And get this, that's just the fee for those load balancers to exist. That's before they've handled a single byte of traffic. It's a huge hidden tax you pay for convenience. The second trap is a really sneaky technical one. By default, Kubernetes might route traffic through an extra hop inside your cluster to find the right pod. When it does that, it performs something called a source NAT, or SNAT. Basically, it rips off the original user's IP address and replaces it with the IP of the node. And just like that, any feature that relies on knowing who your user is, security rules, logging, geolocation, it all breaks. You have to make a choice: perfect load balancing or preserving that critical client info. So how do we fix this mess? How do we get the benefits without the insane cost and the technical headaches? Well, there are two key patterns that the pros use to get total control over their traffic. First, to solve that crazy cost problem, you use something called an ingress controller. Instead of 50 expensive load balancers, you provision just one. That one load balancer then acts as a smart traffic hop, sitting at the front door and directing requests to all 50 of your internal services. Your cost doesn't just go down, it plummets. from nearly $1,000 to less than $20. And to fix that source IP problem, you just add one field to your service: external traffic policy, local. This is you explicitly telling Kubernetes, hey, stop doing that extra hop. Prioritize preserving the original client IP address. And just like that, your application gets its visibility back and can function correctly. But what if you're not in a major cloud? What happens when your cluster is running on-premise, on your own servers, in your own data center? How do you get a load balancer then? For these bare metal clusters, the go-to solution is a project called MetalLB. And it gives you two choices. Layer 2 mode is the easy button. It's basically plug and play, but it creates a single point of failure, and failover can be pretty slow. For real cloud-like performance, you need BGP mode. Now, BGP is the protocol that literally runs the internet. It's more complex to set up, for sure, but it allows your cluster to talk directly to your network routers to provide truly scalable, highly available load balancing. It's the professional choice. So if there's one thing you take away from all this, it should be this: that type load balancer service is an incredibly powerful abstraction. But using it successfully means you have to understand what's actually happening underneath, from the unique dialects of each cloud provider to the hidden costs lurking in the background. Once you master these patterns and understand what's going on, you can really take control of your traffic. You can build systems that are resilient, super performant, and cost-effective. So I have to ask, now that you know what's really happening behind the scenes, will you ever look at a simple type load balancer the same way again? Thanks for watching.